Hello everyone. Today I'm going to give a presentation on our project titled Heart Arrhythmia Detection. So the motivation for this project is basically that cardiovascular disease is one of the leading causes of death, and according to the Cleveland Clinic there are almost 3 million cases of arrhythmia reported every year. Arrhythmia is basically defined as irregular or chaotic heart rhythms such as sustained ventricular tachycardia, and they are of special concern to us because they can cause sudden cardiac arrest or even stroke. So this is our design process. As you can see, we have ECG electrodes. Then the next stage is the instrumentation amplifier. We have filters for filtering out the noise, which is band, pass, and notch. We have the level shift and amplification. We also have the Arduino, which does the analog to digital conversion as well as serial interface. And finally, we have the software code, which is running on LabVIEW on our computers. So these are the stages in our circuit. So the first one is the ECG electrode, which directly connects to the human body. Next, you have the instrumentation amplifier. In the filter stages, you basically have high pass filters, low pass filters, as well as the notch filter. We have a final stage of amplification. We have a level shifting stage for getting it to the right voltage range that the Arduino can accept. We have an ADC, which is basically built into the Arduino microcontroller, and the Arduino is also used for serial interfacing with the computer. And finally, we have implemented all of this as a prototype on the breadboard, and I'll be talking about this shortly. So ECG electrode placement is a careful procedure. It has to be very close to the vein. If it's near the bone where a lot of movement is expected, then you can expect a lot of noise in your signal. And you can see that we have 3 electrodes connected to the human body, one for each arm and one on the right leg. The 2 arm electrodes basically collect the signal data, and the right leg electrode is used for the noise cancellation. So the first stage in our circuit is the instrumentation amplifier. So we have used the INA122 amplifier because it is highly accurate and it has a low noise performance, and it is also very commonly used in biomedical signal acquisition applications. The gain of this amplifier is calculated given the equation on the screen, which is G equals 5 plus 200,000 divided by RG. And RG over here we've taken as 220 ohms for a gain of around 900. So the next stage is the high pass filtering. We've used second order Sallen key high pass filters because they are more accurate and they have a sharper cutoff and frequency domain. They are more complex in design, but as they have a very sharp cutoff, it is very beneficial for us. The cutoff frequency that we have chosen for this application is 0.01 Hz. The next stage is the low pass filter. It's similarly designed to the high pass filter, but over here we've used the cutoff frequency as 500 Hz. Finally, you have the notch filter, which removes the 60 Hz electrical interference. So what we've done is we've used a 20 notch filter for this design, and the equation for calculating the values of R and C is given by Fc equals 1 over 2 pi RC. So the final amplification stage is required because the Arduino's ADC can take inputs only from 0 to 5 volts, and we have found out that in our circuit we needed a gain of about 6.2, so we've used the resistors accordingly. We also have a level shifting stage because the Arduino cannot read negative values. So using this circuit, we have made sure that all the signal values are confined within the positive range. So here you can see this is our breadboard implementation. We have the instrumentation amplifier, which takes its signal from the ECG electrodes. Next we have all the filters, the high pass filter, low pass filter, and the notch. We also have the gain stage, which provides the amplification, and the clamper circuit, which gives the level shifting. So this is the output of our ECG circuit. We have actually connected the electrodes to one of the participants, and you can see that the signal is confined within the positive range. It is well within the range, and there's not a lot of noise in this. So this is the Arduino used for interfacing the analog circuit with the computer. What we've done is we've connected the ECG circuit to one of the analog ADC pins A0, and the code is really simple. What we've done is we've read each value and we are directly sending it to the serial port. So this is the overall setup. You can see that we have 3 electrodes, 2 for the arms and 1 for the right leg to cancel the noise. We have electrode cables that connect the electrodes to the analog circuit. We have 2 9-volt batteries. We have the analog circuit itself, an Arduino for the ADC as well as serial interface, and an Arduino USB cable for connecting the Arduino to the computer. So the next stage is using the LabVIEW software to actually recognize the ventricular tachycardia. So what we've done is we have a basic block diagram which basically acquires the signal, it processes it, then displays the waveform, does some feature detection or feature analysis, and displays all the results on the screen in the form of a GUI. So the first stage is the filtering and displaying the signal. So what we've done is we can either simulate the signal using one of the toolboxes, or you can acquire a new waveform from the external analog device. So our band pass filter is in the range of 0.01 Hz to 500 Hz. The notch filter is 60 Hz, and we've also used a wavelet transform for removing the baseline wandering. So as you can see in this figure, the first figure is very noisy. We haven't filtered it, but once we've applied all the filtering, like the high pass filter and the low pass filter, you can see that the noise has been removed completely. And in this figure you can see the frequency spectrum of our signal, and you can see that there's a peak in 60 Hz on the left hand side, and after applying the notch filter you can see that it has been removed completely. And in this figure you can see how the baseline wandering affects our results. You can see that in the first figure the ECG signal is drifting from its baseline, whereas after applying wavelet filtering you can see that it's actually very steady. So finally we have a feature detection block. So we've used the LabVIEW's biomedical toolkit for feature extraction. We have used this for detection of various characteristics of the ECG waveform, such as the P, the QRS waveform, the R, T, as well as some time intervals such as interpeak, P and T interval, P and R interval. And we've also used this toolbox for calculating statistical parameters such as mean and standard deviation. It also gives us the average and instantaneous heart rate. So let's try to understand what ventricular tachycardia actually is. Ventricular tachycardia is defined when the heart rate is above 100 beats per minute, the P wave is completely absent, the QRS complex exceeds 120 milliseconds, and there are 3 or more consecutive VPCs, and the RR interval is irregular. So this is our VT detection algorithm according to the steps that we have mentioned before. So we obtain the waveform features, we check if the P wave is present or not. If it's not present, we check if the QRS complex is longer than 120 milliseconds. If this is true, then we check if the VPC is greater than 3. We check if the heart rate is greater than 100 beats per minute. And if all these conditions are satisfied, then we know that ventricular tachycardia is occurring. So these are our results and future work. So we've been able to detect 97.6% sensitivity of the simulated ventricular tachycardia waveforms. But when we test this against the MIT BIH database, it gives a fairly poor detection. It requires additional refinement to measure the specificity and sensitivity when identifying the database waveforms with annotated VT events. Improving the P wave detection is of course one of our top priorities, and improving the VPC detection for an inverted QRS complex events is also a priority. So these are some of the references we have used in our project. Feel free to go through them and gain more information about our project. If you have any questions, you can please tweet your questions using the following hashtag. Thank you so much.